Before we get into electrolysis, let's review the structure of a voltaic cell so we can compare it to an electrolytic cell. So a voltaic cell uses a spontaneous redox reaction to produce an electric current. So if we start at our zinc electrode, solid zinc turns into zinc 2 plus ions. So solid zinc turns into zinc 2 plus ions. And an atom of zinc would have to lose 2 electrons to turn into zinc 2 plus. So loss of electrons is oxidation, and oxidation is occurring at our zinc electrode. So the zinc electrode must be our anode. Remember, oxidation occurs at the anode, and you can remember that by anox. The zinc electrode is our source of electrons, so this is our negative electrode, and those electrons move in our wire to produce an electric current. When those 2 electrons reach our copper electrode, we know we have copper 2 plus ions in solution. So copper 2 plus ions in solution. And when those copper 2 plus ions gain those 2 electrons, copper 2 plus turns into solid copper. So copper forms at our copper electrode here. So this is reduction. Gain of electrons is reduction. So reduction is occurring at our copper electrode, making this the cathode. Remember red cat. Red cat is how to remember that one. So the copper electrode must be our positive electrode. This reaction is spontaneous. The standard cell potential, E0, is positive 1.10 volts. Remember, a positive value for your cell potential means a spontaneous reaction. So we produce an electric current. Let's compare that voltaic cell to an electrolytic cell, so on the right. An electrolytic cell uses an electric current to drive a non-spontaneous redox reaction. So if we look at the overall reaction here, we're starting with solid copper and zinc 2 plus ions in solution, and we're going to copper 2 plus ions in solution and solid zinc. So this is the reverse of the reaction we just talked about. Right? The reactants for this reaction were the products for this reaction. To find the standard cell potential, all we have to do is take the negative of this cell potential because we just reversed the reaction. Right? So if we reverse the reaction, we just change the sign. So the cell potential, the standard cell potential would be negative 1.10 volts. A negative value for your cell potential means a non-spontaneous redox reaction. So this doesn't occur on its own. Solid copper doesn't just turn into copper 2 plus, and zinc 2 plus doesn't turn into solid zinc. It needs some help in order to do that. It needs an external voltage source, like a battery, to drive this reaction and force it to happen. So we need a battery here. Let's put in a battery in our little circuit. So we have a battery. We need the negative terminal to be on the left side and the positive terminal to be on the right side. So this is our voltage source. And we need at least 1.10 volts to force this reaction to occur. And in practice, it turns out to be more than 1.10 volts. So our negative terminal of the battery is where we get electrons. So electrons come out of the negative terminal of the battery, right, and deliver electrons to the zinc electrode. So electrons are forced onto the zinc electrode. So let me draw in here 2 electrons. And now we have zinc 2 plus ions in solution. Those zinc 2 plus ions have an opportunity to be reduced. If those zinc 2 plus ions gain those 2 electrons, zinc 2 plus gains 2 electrons and turns into solid zinc. So solid zinc forms on our zinc electrode. So zinc 2 plus gaining 2 electrons to form solid zinc is reduction. Gain of electrons is reduction. So this time, reduction is occurring at our zinc electrode, and reduction occurs at the cathode. So the zinc electrode is our cathode. So once again, red cat. The zinc electrode is more negative, right? So we've had electrons forced onto the zinc electrode. That makes this our negative electrode. The battery is pulling electrons away from the copper electrode. So the copper electrode is losing electrons. So electrons are going toward the battery here. So electrons are going toward the positive terminal of the battery. That makes the copper electrode relatively positive. So this is our positive electrode. And this is the site, this must be the site of oxidation. Right, so solid copper turns into copper 2 plus ions. So solid copper turns into copper 2 plus ions. So we have solid copper turning into Cu2 plus. And so we're losing 2 electrons in order to do that. So solid copper turns into copper 2 plus. We lose 2 electrons. Loss of electrons is oxidation. So oxidation occurs at our copper electrode this time. And that makes this the anode because oxidation occurs at the anode, so anox. So the copper electrode loses mass over time. So you can see the difference between a voltaic cell and an electrolytic cell. So a voltaic cell created a current because we had a spontaneous redox reaction. But for an electrolytic cell, we had a non-spontaneous redox reaction. So to get it to occur, we needed a current. We needed an external voltage source. Let's point out the fact that the signs of the electrodes are opposite for voltaic and electrolytic cells. For example, let me use a different color over here. We can see that the anode, right? The anode was the zinc electrode, and this was our negative electrode here. And that's because the zinc electrode, right, was our source of electrons. So this makes that our negative electrode. But over here, the negative electrode is our cathode because electrons are forced on it by the battery. So the signs of the electrodes are opposite for voltaic and electrolytic cells. Notice for an electrolytic cell, the negative electrode matches up with the negative terminal of the battery, and the positive electrode matches up with the positive terminal of the battery. So that's a good way to remember which electrodes are which in an electrolytic cell. Just look at the battery and you can figure it out.